objects which have mass are attracted to each other. This force of attraction is dependent on the masses of the two objects and the distance they are apart. If two people are standing next to each other, there will be a force of attraction between them, but this will be so small as to be unnoticeable. The force produced by the Earth is so much larger because the mass of the Earth is so much larger than a person. Hopefully you've had a play with the simulation. In this sim you can change two things: the masses of the two spherical objects and the distance that they are apart. You should have observed that the size of the forces, which we see up here, on the two objects is always the same. So the size of this arrow is the same as the size of this arrow. You can increase the size of the force by increasing the size of the masses. Increasing the size of either mass increases the force. So if I increase this one, increase the force. If I increase this one, it increases the force. You can also increase the size of the force by reducing the distance between the two objects. We saw from our sim that the size of the force of attraction is proportional to the product of the two masses. That is, the two masses are multiplied together. We also saw that increasing the separation of the two masses reduces the force of attraction. Therefore, they are inversely related. In fact, the force goes as 1 over the distance squared. This means that if the distance is doubled, then the force is reduced to 1/4 of its original value. And if the distance is tripled, the force is reduced to 1/9 of the original value, etc. We can now write a mathematical expression. The force is proportional to the product of the two masses. Let's call them M1 and M2. Force is also inversely proportional to 1 over the distance squared. Now it's usual to write the distance with the symbol r, and that's the distance between the centre of the two masses. And we can see from above that it goes as 1 over r squared. So I'm going to write r squared on the bottom. We also need a constant, because we only have said that the force is proportional to these terms. Okay, so we're going to have a constant multiplied by this thing here. Now, in this case, the constant is given a symbol g. This is called the universal gravitational constant. Now let's take a look at the concept of fields. We will come across other fields in this course, namely electric fields and magnetic fields. Here we're going to be concentrating on gravitational fields. So let's have a look at the introduction here. A field is a region of space where the object experiences a force. Objects with mass produce a gravitational field. When another object with mass is in this field, it will experience a force. Field lines show the direction of this force at any position. The spacing of field lines indicates the strength of the force. Field lines which are close together indicate a strong field. Now below is a diagram showing the field at the surface of the Earth. As the field lines are on this scale uniformly spaced, we say the gravitational field is uniform. Okay, so I just want to show you on this diagram that these lines pointing down are called the field lines. And we have an object with mass in this field, gravitational field, and it experiences a force in the direction of the field lines downwards. Now the spacing of these field lines is the same everywhere, and that shows us that this object, no matter where it is placed, it will experience the same force towards the Earth. What you should have drawn is the following that I've shown in this diagram, hopefully a bit neater than mine. Field lines should all be pointing towards the centre of the spherical object, and this is called a radial field, as opposed to the uniform field that we saw above. Note that the field lines become more spaced out as you move away from the body. This indicates that the field strength is decreasing as you move away. Next we will discuss gravitational field strength. Okay, let's have a look at the introduction. You'll be most familiar with this symbol G, and it stands for, you've probably come across it as the acceleration due to gravity. As we'll see, there's an equivalence below. The gravitational field strength is the force experienced by a unit test mass, so essentially a 1 kilogram mass. What's the force on that placed at a certain position? The symbol for gravitational field strength is G, and G is the force per unit mass, so force divided by mass. And so you can see that force is in newtons and mass is in kilograms, so the units are going to be newtons per kilogram, or newtons, kilograms, -1. Now actually the newton is not a base unit. So if you think of the formula F equals ma, you can see that the newton is actually equivalent to a kilogram times a meter per second squared. So using these are all base units, the kilogram, the meter and the second. So this is the base unit actually for force. So if we put that in, substitute that in for the newton here, we'll end up with kilograms, meters per second squared, all over kilograms. And basically the kilograms will cancel, and so we end up with the unit meters per second squared, or you like to write it the other way, meters seconds to the -2. And you can see, you recognise this unit as the unit for acceleration. So in fact, the gravitational field strength in newton per kilogram is actually equivalent to the G, the acceleration due to gravity, in meters per second squared. Okay, we want to find out an expression for G using this formula here. Well, we know that that G is the force per unit mass, so we're going to put force over mass. In this expression here, let's imagine that we're going to call M1, we're going to call that capital M, and we're going to call M2 is going to be our test mass, and we're just going to leave that as 1 kilogram. And what we're interested in is what is the gravitational field strength caused by this body M1. So we're going to put our test mass at a certain distance, r, okay, to find out what g is at that position. So we end up with an expression here is gm times 1, because we put m2 as 1, over r squared, which is the distance. Okay, and so we can see that our final expression is going to be g equals gm over r squared. So this is the gravitational field strength at a distance r from a mass